Welcome viewers to the fifth lecture of a series of NPTEL lectures on integral equations. In the last lecture we have discussed about the successive approximation method for solving Volterra integral equation of second kind. Now, in today's lecture we are going to discuss about two different techniques of solving Volterra integral equation of first kind, and one method is Laplace transform method and second one is the series solution method. So, just for a quick recapitulation, I start with the definition of Laplace transform, because we have to be specific about the notations we are going to use to solve the Volterra integral equation of the first kind. So, suppose f x is a function which is defined for all x greater than 0, and this function is of exponential order. Now, before going to the definition of Laplace transform, we try to understand what is the meaning of functions of exponential orders. This function f x which is defined for all x greater than 0. Now, if there exist real constants capital M, gamma and t, these are all greater than 0, such that the function f x when multiplied with e to the power minus gamma x, then its modulus is less than m for all x greater than capital T. f x is a function which is defined for all x greater than 0. There exist three positive constants, one is m, second is gamma, third is capital T, such that e to the power minus gamma x f x, its modulus is less than m for all x greater than equal to t. If this happens, then we can say f x is a function of exponential order, and order of this given by gamma as x tends to infinity, or briefly we can say this function is of exponential order. Actually, if a real valued function f x for x greater than 0, it satisfies the exponential order criteria, then only its Laplace transform exists, and Laplace transform of this function f x is denoted by L of f x, and oftenly we denote this by f of alpha, and is defined by integral 0 to infinity e to the power minus alpha x f x dx, where alpha is a positive real constant. Now, convergence of this integral depends upon the exponential order of the function, and actually if this function f x is sectionally continuous over the interval 0 less than equal to x less than equal to t, and is of exponential order then this Laplace transform exists. Now, once we use this Laplace transform to convert f x to f alpha, that means we are relating this function of x to a real variable function that is constant of parameter alpha, then of course using the inverse Laplace transform we can get back this function f x from where we have obtained this f alpha. Now, most of the time we use the pair of Laplace transform table, that is f alpha and f x, capital F alpha and f x, such that when we consider the inverse Laplace transform of f alpha, we will be get back the function f x, and according to the notation we use L inverse f alpha, that is equal to f x. So, this actually implies and implied by, if L of f x this is equal to f alpha, then L inverse f alpha this is equal to f x. Now, we are going to use this particular Laplace transform in order to solve Volterra integral equation of some special type, and before going to that I just like to recall another idea, that is convolution of two functions. Convolution of two functions. Let f1 x and f2 x, these are two real valued functions defined for all x greater than 0, and both of them satisfies the criteria for exponential order, and their Laplace transforms are denoted by L of f1 x, this is equal to say f1 alpha, and L of f2 x, this is equal to f2 alpha. These are the Laplace transform of f1 x and f2 x. Now, convolution of these two functions is denoted by f1 star f2 and defined by integral 0 to x f1 x minus s f2s ds. This is actually called convolution of two functions f1 x and f2 x, which is denoted by f1 star f2. You have to keep in mind this convolution property is actually commutative. We can easily prove f1 star f2 is equal to f2 star f1 just by changing the variable. If we substitute x minus s equal to u, you can easily prove this is equal to 0 to x integral f2 x minus s times f1 s ds. Now, interesting point is that if we consider the Laplace transform of the convolution of these two functions f1 star f2, then it will give us the product of the Laplace transform of the functions L of f1 x multiplied by L of f2 x. So, that means this is going to be f1 alpha multiplied by f2 alpha, and most important part is that if we have a function of alpha which can be expressed as product of two functions of alpha like f1 alpha and f2 alpha, such that from the table we know what are the functions for which f1 alpha and f2 alpha are the Laplace transform, then inverse Laplace transform of f1 alpha and f2 alpha will be the convolution of two functions f1 and f2. So, that means L inverse f1 alpha multiplied by f2 alpha, this is equal to f1 star f2. So, that is equal to integral 0 to x f1 x minus s f2 s ds. This is actually formula related with convolution of two functions and the Laplace transform. Now, we are going to use this Laplace transform method in order to solve Volterra equation of second kind, but of course, for those Volterra equations of second kind, if lower limits is starting from 0, that means instead of a if we have 0 and the kernel of the function is actually a function of difference of two variables, that is x minus s, then only we can apply this Laplace transform method. So, to be specific in terms of mathematical notations, this is your given integral equation y x equal to f x plus lambda integral 0 to x k of x comma s y s d s. So, first criteria is lower limit should be equal to 0. Now, if capital K x, this is actually a function of small k of x minus s, if this condition is satisfied by the kernel of the function, then only we can apply the Laplace transform method. So, in this case you have to keep in mind the applicability of this technique to find out the solution of the integral equation depends upon the lower limit whether it is 0 or not, number 1, and secondly kernel is of actually particular type k of x minus s. And if this condition is satisfied, then first I describe here how to proceed to find out the solution of the problem. Suppose Laplace transform of y x, this will be denoted by capital Y alpha. As usual, Laplace transform of f x is denoted by capital F of alpha, and Laplace transform of small k x, this will be denoted by chi of alpha. This is the notations, and actually you can try to understand that whenever k x comma s is a function of the form k of x minus s, then integral 0 to x k x comma s y s d s, this is nothing but the convolution of the function small k x and the unknown function y s. So, that means specifically we can write if k x comma s satisfies this criteria, then integral 0 to x k x comma s y s d s, this is actually equal to convolution of k x star y x. So, then we can take Laplace transform of the given integral equation. So, taking Laplace transform of this equation, call it 1, we can get y alpha is equal to f alpha plus lambda times Laplace transform of convolution of k star y, this is small k, keep in mind, not capital K, and this is equal to actually f alpha plus lambda times chi alpha multiplied by y alpha. So, solving for y alpha, we can find y alpha, this is equal to f alpha divided by 1 minus lambda chi alpha, with the hypothesis that lambda chi alpha, this is not equal to 1. So, once we have this result, that is y alpha is equal to f alpha by 1 minus lambda times kappa alpha, then we can solve it by using inverse Laplace transform method to get y x is equal to L inverse of y alpha, and that is equal to inverse Laplace transform of f alpha divided by 1 minus lambda chi alpha. So, once we are able to find out inverse Laplace transform of this algebraic expression in terms of alpha, then actually we can find the solution of the given problem as y x. Now, we look at some illustrative example to understand this method. You can recall that this problem we have solved earlier by using other technique, that is y x is equal to x minus integral 0 to x x minus s y s d s. So, clearly you can understand that k x comma s is actually x minus s. So, if we write in terms of small k x, so then small k x is nothing but x. And here from the structure of the equation f x is equal to x, k x equal to x. So, we need only the knowledge about the at this moment Laplace transform of x, and that is nothing but 1 by alpha square. So, using this result Laplace transform of x equal to 1 by alpha square, if we take the Laplace transform of the given integral equation, then we can find y alpha, this is equal to 1 by alpha square minus 1 by alpha square multiplied with y alpha. This is the result. Actually, this is coming from the concept that Laplace transform of integral 0 to x, x minus s y s ds means we are taking the Laplace transform of convolution of two functions x and y x. Now, Laplace transform of x is 1 by alpha square, Laplace transform of y x we assume to denote it by capital Y alpha, then Laplace transform of the integral 0 to x, x minus s y s ds, this expression results in 1 by alpha square y alpha. So, solving for y alpha, we can find y alpha, this is equal to 1 by alpha square, and from the table we can find L of sin x, that is Laplace transform of sin x, is equal to 1 by alpha square, and hence L inverse 1 by 1 plus alpha square, that is equal to sin x, and hence taking inverse Laplace transform of y alpha, we can find y x, this is equal to sin x. This is actually solution of the given integral equation, that is first example. Now, we consider one more example, example 2. I am going to consider this example for the reason that here in order to apply inverse Laplace transform, we have to utilize the fast shifting property of inverse Laplace transform. So, first of all we write the problem. Problem is y x equal to x plus 2 integral 0 to x cosine of x minus s y s ds. Now, already I have mentioned that Laplace transform of x is 1 by alpha square, and here I can mention Laplace transform of cosine x, this is equal to alpha by 1 plus alpha square. This is the Laplace transform of cosine x. This is needed because here 0 to x cosine x minus s y s ds is again convolution of two functions, that is cosine x and y x. So, taking Laplace transform of the given integral equation, we can write y alpha, that is equal to 1 by alpha square plus 2 alpha by 1 plus alpha square, this multiplied with y alpha, and transferring this particular term onto the left, and after rearranging we can find y alpha, this is equal to 1 plus alpha square divided by alpha square into alpha minus 1 whole square, and we can rearrange this term first into the form that is 1 by alpha square times alpha minus 1 whole square plus 1 by alpha minus 1 whole square, and using the method of partial fractions we can write this is equal to, after some algebraic calculation, this will be equal to 2 by alpha plus 1 by alpha square minus 2 by alpha minus 1 plus 2 by alpha minus 1 whole square. So, this will be the expressions. Now, we need these results, that is L of 1 equal to 1 by alpha. Actually, inverse Laplace transform of 1 by alpha will be then 1. already we know the result, that is Laplace transform of x, that is equal to 1 by alpha square. So, inverse Laplace transform of 1 by alpha square will be x, and thirdly Laplace transform of e to the power a x, this is equal to 1 by alpha minus a. So, that means inverse Laplace transform of 1 by alpha minus 1 is going to be e to the power x, and now we have to be careful for the inverse Laplace transform for 1 by alpha minus 1 whole square, and here actually we need to apply the first shifting property of inverse Laplace transform. It states that if L of f x, this is equal to f alpha, then inverse Laplace transform of f alpha minus a, this is equal to e to the power a x multiplied by f x. So, actually we apply this result in order to find out this inverse Laplace transform of 1 by alpha minus 1 whole square. So, if we consider f alpha equal to 1 by alpha square, then 1 by alpha minus 1 whole square is coming out to be f of alpha minus 1. So, with a equal to 1, and then using this first shifting property we can write this is equal to e to the power x into x, because this e to the power x coming from the part e to the power a x, and this x is stands for f x, because this 1 by alpha square is actually Laplace transform of x. So, L inverse 1 by L minus 1 whole square is equal to x e to the power x. So, therefore, from y alpha is equal to 2 by alpha plus 1 by alpha square minus 2 by alpha minus 1 plus 2 by alpha minus 1 whole square. If we take the inverse Laplace transform, then we will be having y x, this is equal to 2, inverse Laplace transform 1 by alpha is 1 plus x here minus 2 e to the power x plus 2 x e to the power x. So, answer will be required answer is 2 plus x plus 2 e to the power x into x minus 1. So, this is the solution for the given Volterra integral equation of the first kind. Next we consider one more example. This is little bit interesting only for the reason that when we solve this equation, then you can find that solution of the given equation is completely related with the non-homogeneous part of the integral equation involved with the given problem. This example 3, it states that y x is equal to f x plus 3 integral 0 to x e to the power x minus s y s ds. So, here e to the power x minus s is involved. So, that means first function f 1 x is e to the power x and second function is y s, and already we have noticed that Laplace transform of e to the power a x is equal to 1 by alpha minus a. So, therefore, Laplace transform of e to the power x is going to be 1 by alpha minus 1. So, here if we take the Laplace transform of both the sides, this is actually convolution of e to the power x and y x. So, taking Laplace transform, we can find y alpha, this is equal to f alpha plus 3 divided by alpha minus 1, this multiplied with y alpha, this one. Now, if we simplify it, then we can find y alpha, this is equal to f alpha times alpha minus 1 divided by alpha minus 4, and writing the numerator into the form alpha minus 4 plus 3, we can find from here that is f alpha plus 3 f alpha multiplied with 1 by alpha minus 4. So, now f alpha comes into this part, and from here if we take the inverse Laplace transform of the both sides, then y x is equal to inverse Laplace transform of f alpha plus 3 f alpha multiplied with 1 by alpha minus 4. So, this is equal to f x, because we have denoted the Laplace transform of f x by capital F alpha. So, inverse Laplace transform of capital F alpha will be f x plus 3 convolution of e to the power 4 x with f x. This is actually the convolution of these two functions. So, writing the formula for convolution of two functions, we can find this is equal to f x plus 3 integral 0 to x e to the power 4 x minus s f s ds. So, this problem is little bit interesting only from the for the reason that given integral equation is y x equal to this one. Now, once this f x is known, so result of the integral equation is completely depends upon this integral. So, once f x is known, so substituting f x here we can evaluate this integral, and then this will gives us the desired result for the given problem. Next we consider the series solution method. Series solution method for Volterra integral equation of the second kind. Again, in this case we restrict ourselves problems of the type y x equal to f x plus lambda times integral 0 to x k of x comma s y s ds. So, here only lower limit 0, this is required, and there is no restrictions for y x comma x, that means no particular format for this kernel is required, as we have seen that in case of applying Laplace transform it need to be k x comma s is a function of x minus s, but at a later stage I will make some remark that in which cases we can think about solution of the integral equation into the with the help of series solution method. So, the point is that we are assuming that solution of these equations can be expressed as a power series around x equal to 0. So, we are assuming solution in the form y x is equal to sigma n runnings from 0 to infinity C n x to the power n. This is our targeted form of the solution. So, that means if we are going to solve this equation by series solution method, then we have to substitute this expression into the given equation. Then we can integrate this k x comma s multiplied by this series, it will be actually converted into term by term integration, and then using the Taylor series expansion of f x we have to solve for C 0, C 1, C 2 and so on, and actually we have to derive some recurrence formula from where once we know the values of some initial C 0, C 1, C 2, using the recurrence formula we will be able to calculate all C n's. Now, the method is, if you substitute this series into this given problem, so it is equal to n runnings from 0 to infinity C n x to the power n, this is equal to f x plus lambda times integral 0 to x k x comma s sigma n runnings from 0 to infinity C n s to the power n, this is the expression for y s ds, and this actually implies we will be having C 0 plus C 1 x plus C 2 x square plus dot dot, this is equal to f x plus lambda times c 0 integral 0 to x k x comma s ds plus lambda times c 1 integral 0 to x k x comma s s ds plus lambda times c 2 integral 0 to x k x comma s s square ds plus dot dot. Now, using the continuity of this kernel k x comma s over the squared domain 0 to say some beta cross 0 to beta, we can find that this summation and integral sign can be interchanged, and then after expanding we will be having this type of infinite series consist of summation of these integrals, and after expressing f x in terms of Taylor series, we can get this expression which is valid for all x. Then collecting the coefficients of equal powers of x, we can find a system of equation, and solving those system of equation, once we find out C 0, C 1, C 2 and so on, then we can have the solution for the given integral equation. So, in order to understand this method, we consider two examples. First example is y x, this is equal to x minus integral 0 to x x minus s y s ds. So, of course, this equation we just solved with help of Laplace transform method, and just to verify that whether we are getting same solution or not, we going to apply here the series solution method. Now, you can see that if we use series solution method here, so substituting the series, that is sigma n runnings from 0 to infinity C n s to the power n, we have to integrate the integrals of the form 0 to x x minus s ds, then 0 to x x minus s multiplied by s ds. So, in general that means 0 to x x minus s multiplied by s to the power n ds. So, for each n ranging from 0 to infinity, we will be integrating the integrand, that is x into s to the power n minus s to the power n plus 1. It is very easy to integrate. So, this gives us some sort of indication that although we can apply the Laplace transform method to solve this equation, and then we can going to apply the series solution method whenever this integrand is easy to handle, or it will be easy to integrate this integrand coming out after substituting sigma C n s to the power n. So, here substituting this series y x is equal to sigma n runnings from 0 to infinity C n x to the power n, we can find on the left hand side C 0 plus C 1 x plus C 2 x square plus dot dot. These are the terms, and here we do not need to think about further, because f x is simply x, and then minus C 0 integral 0 to x x minus s ds minus C 1 integral 0 to x x minus s s ds minus dot dot, general term is C n integral 0 to x x minus s multiplied with s to the power n ds minus dot dot. Here this should not be plus, rather it will be minus here. After integration, we can find this is equal to x minus C 0 x into x minus x square by 2 minus C 1, this is x into s. So, that means x into x square by 2 minus s squared ds. So, that is x cube by 3 minus dot dot. In this way, general term will be minus C n x into x to the power n plus 1 by factorial n plus 1 minus x to the power n plus 2 divided by n plus 2 minus dot dot. So, this is actually the general term what we will be getting after integration. So, this is actually equal to x minus C 0 x square by 2 minus C 1 x cube by 2 into 3, and here as a general term we will be having minus C n x to the power n plus 2 divided by n plus 1 multiplied with n plus 2. I am sorry, here it will be n plus 2. So, term after C 1, it is clearly it will be minus C 2 x to the power 4 divided by 3 into 4 and so on minus dot dot. So, if we equate first few terms, on the left hand side we have C 0, there is no constant term on the right hand side. So, therefore, C 0 this is equal to 0. So, this result we are getting by equating constant term from both the sides. Next, if we look at the coefficient of x, on the left hand side coefficient of x is C 1 and on the right hand side coefficient of x is 1. So, therefore, equating the coefficient of x we can find C 1 this is equal to 1. Next, square term C 2 x square this is equal to minus C 0 x square by 2. So, that means C 2 this is equal to minus C 0 by 2, this implies C 2 equal to 0 because C 0 equal to 0. Similarly, if we equate the coefficient of cubic term, here we have C 3 x cube and on the right minus C 1 x cube by 2 into 3. So, therefore, C 3 is equal to minus C 1 by 2 into 3. So, this is equal to minus 1 by 2 into 3, and recurrence formula can be obtained in this way. On the left hand side coefficient of x to the power n plus 2 is actually C n plus 2, and here we have already observed that coefficient of x to the power n plus 2 on the right hand side is minus C n divided by n plus 1 whole multiplied by n plus 2. So, therefore, equating the coefficient of x to the power n plus 2 from both sides, we will be having minus C n divided by n plus 1 into n plus 2. So, using this recurrence formula and the results C 0 equal to 0, C 2 equal to 0, we can find C 4 equal to C 6 equal to C 8, all these coefficients exactly equal to 0. We have already obtained C 3, then C 5, this is going to be minus C 3 divided by 4 into 5. So, after substituting this expression minus 1 by 2 into 3, we can write this is equal to 1 by factorial 5, then C 7 will be minus C 5 divided by 6 into 7. So, this is equal to minus 1 by factorial 7 and so on. So, if we substitute these expressions into the series that we have assumed, then we can find y x this is equal to x minus x cube by factorial 3 plus x to the power 5 by factorial 5 minus x to the power 7 by factorial 7 plus dot dot. So, that means we are getting the Maclaurin's infinite series expansion for sin x. So, therefore, by using the method of series solution, we are getting the solution y x is equal to sin x for the given problem. Last example that I am going to consider here, that is little bit interesting only for the reason that although we are assuming a infinite series solution for the given problem, but after solving the problem you can see that the solution is actually a polynomial, and the problem is y x, this is equal to 1 plus x minus 2/3 x cube minus x to the power 4 by 2 plus 2 integral 0 to x s y s ds. Again look at the kernel involved with this particular problem, it is only s here. So, that means if we use this particular series assumption about the existence of series solution, that is 0 to infinity c n x to the power n. So, after substitution for the general term actually we need the integral of s to the power n plus 1. So, this is very easy to integrate and obtain the result into the closed form. So, most of the time we will be adopting this series solution technique whenever after multiplying s to the power n by the kernel involved with the integral equation, it is easy to handle. That is the some sort of you can say suggestion where we can apply this series solution method. Now, if we substitute this series into this given problem, then we will be having C 0 plus C 1 x plus C 2 x square plus C 3 x cube plus dot dot. This is equal to 1 plus x minus 2/3 x cube minus x to the power 4 by 2 plus 2 sigma n runnings from 0 to infinity integral 0 to x s to the power n plus 1 ds. So, after integration this is coming out to be 1 plus x minus 2/3 x cube minus x to the power 4 by 2 plus 2 sigma n runnings from 0 to infinity c n x to the power n plus 2 divided by n plus 2. Here I have missed the c n term, this is c n. So, that means we have this particular series. Now, this problem is little bit interesting from two sides. Number 1, up to x to the power 4 we have one sort of relations between these cj's, and for x to the power n plus 2 by n plus 2, whenever this n plus 2 is greater than 4, then we will be having another set of relations. So, first of all we have to find out first 4 constants C 0, C 1 up to C 4 carefully, because on the right hand side we have these expressions involved with the part f x and rest of the part does not interfere here. So, that means no term from x will interfere with the series whenever the index is 5 and higher. So, this is equal to 1 plus x minus 2/3 x cube minus x to the power 4 by 2, and if we substitute n equal to 0 here. So, this series started giving contribution from x square and onwards. For x square we will be having C 0 x square, substituting n equal to 0 we will be having x square from here, substituting n equal to 1 we will be having 2/3 C 1 x cube, this is the second term from this series, then plus half C 2 x to the power 4, this is the term we get by substituting n equal to 2, plus rest of the term will be of the form 2 by 5 C 3 x to the power 5 and so on. Now, if we just compare the constant terms from the both sides. So, first of all we will be having C 0, this is equal to 1, because on the left hand side it is C 0 and on the right hand side we have only 1 here. Then collecting the coefficient of x from both sides, we can find on the left it is C 1, on the right it is x only. So, therefore, C 1 this is equal to 1. Next we look at the coefficient of x squared term. Here it is C 2 and in this f x part there is no x squared term and x squared term is coming from this part. So, that is C 0. So, coefficient of x square on the right hand side it is C 0, on the left hand side it is C 2. So, equating we can find C 2 this is equal to C 0 and already we have obtained C 0 equal to 1. So, this C 2 coming out to be 1. Next we collect the coefficient of x cube. On the left hand side coefficient of x cube this is equal to C 3. On the right hand side f x part contains minus 2/3 x cube. So, minus 2/3 is coming from here and here we will be having plus 2/3 C 1. So, this is minus 2/3 plus 2/3 this multiplied by C 1. Already we know the value of C 1. So, after substituting this C 1 value we will be having this is identically equal to 0. Last but one, that is coefficient of x to the power 4, on the left hand side it is C 4. So, from left hand side we will having C 4 and from the right hand side this is minus half and plus C 2 by 2. Here coefficient of x to the power 4 is C 2 by 2. So, this gives minus half plus C 2 divided by 2, we already have C 1 equal to 1. So, this is equal to 0. So, two consecutive terms C 3 and C 4 this is equal to 0. Now, on the rest of the terms, that is terms of the form x to the power 5 and higher, on the left hand side we will be having C 5, C 6 and so on. These are the coefficients of x to the power 5, x to the power 6 and so on, and on the right hand side this is nothing but 2 C n divided by n plus 2, this is the coefficient of x to the power n plus 2. So, that means collecting the coefficient of x to the power n plus 2 from the both sides in order to get the recurrence relation, we can write recurrence relation is coming out to be C n plus 2 that is equal to 2 C n divided by n plus 2. Now, remember this result is valid for n greater than equal to 3, because already we have equated the coefficient of constant term from both sides, coefficient of x from both sides up to coefficient of x to the power 4 from both sides, and this we have done only for the reason the f x part contains term up to the order x to the power 4. So, from x to the power 5 and onwards we can write the general recurrence formula. So, from the left we are getting the coefficient of x to the power n plus 2 is simply C n plus 2, and on the right hand side coefficient of x to the power n plus 2 is actually 2 C n divided by n plus 2. Now, this result is valid for n greater than equal to 3. So, clearly from C 3 equal to 0 and C 4 equal to 0 you can find C 5, C 6 is equal to C 7 and onwards all these coefficients are identically equal to 0. C 5, C 6, C 7 are all this quantity equal to 0. Already we have C 3, C 4 this is equal to 0. So, although we have assumed an infinite series as a solution of the given problem, but we landed at a solution that is given by 1 plus x plus x square. There is no other terms involving higher powers of x. So, this is clearly a polynomial which is a solution for the given problem, and I hope you have experienced these type of situations will appear in case of ordinary differential equations also, and these Volterra integral equations is most of the time we obtained it by converting the linear ordinary differential equations, that is initial value problems, converted to Volterra integral equations. And therefore, in case of ordinary differential equation we have the experience that sometimes we are trying to find out solution which are assumed to be an infinite series, but ultimately solutions are comes out to be a polynomial. So, just for a quick recapitulation what we have done today. So, first of all we have defined what is Laplace transform for a function with exponential order, and then we have considered the convolution of two functions f1x and f2x, and Laplace transform of convolution of two functions f1 and f2 is nothing but the product of the Laplace transform of these two functions. And this Laplace transform method can be solved can be used to solve the Volterra integral equation of first kind whenever this kernel k x comma s is of special type, that is it is a function of x minus s only. And in the illustrative example we have seen, in one case we have used x minus s as the kernel. So, therefore, k x was equal to x. Secondly, k x comma s is cosine x minus s. So, that means small k x is nothing but cosine x. And third problem that we have considered, that kernel k x minus s is actually e to the power x minus s. So, for those problem we can apply this Laplace transform method to solve it, and we need the formula for inverse Laplace transform from any table of Laplace transform. We can get this result to find out the ultimate solution of the given problem. And then we have considered the series solution method, where we are assuming solution into the form y x equal to n runnings from 0 to infinity c n x to the power n. After substituting this expression into the integral equation, we are having some recurrence relation equating the general form of the x to the power n term. Most of the time we have used the coefficient of x to the power n plus 2 from the both sides, and of course, you have to be careful about the Taylor series expansion for f x. Fortunately, the examples that I considered here, those are having finite number of terms in the Taylor series expansion for f x, and in the last example we have observed that this solution results in a polynomial rather than an infinite series. So, thank you for your attention.